Okay, so good evening everyone. I am Shivani Dhok and I welcome you all to the second tutorial of this course, that is Introduction for Wireless and Cellular Communication. And like every time, this week's tutorial will be divided into two parts. First, I'll discuss or rather recap the contents that were covered in this particular week, and then followed by the questions which are related to this week's content. I'll try to keep questions which are related to the assignments or in your for the course or weekly assignments, but obviously they won't be the same questions. And at any point of time, if you have any questions, you can unmute yourself and ask the queries. Another thing is, I think the link for the YouTube videos, I have pinned it. After every lecture, I'll upload this recorded session to my YouTube channel, and the link is also shared to you by the NPTEL people in your portal. So bottom left corner you can find problem solving session tab. In that, if you go, you will find a link to every week's tutorial, as well as you will find a link to a folder which will give you that particular week's or rather every week's notes as well. Like whatever slides I'm using, that those slides also will be uploaded just after the session. So if you don't want to write anything and just concentrate on listening what I'm speaking, then feel free to do that, because notes will be shared with you. Then okay, so let's start with the recap of week 2 content. So week 2 is the week where we formally started to look at the technical aspects of this course. But initial weeks, we still looked at a superficial overview of various things, such as what does your mobile number or MSISDN number imply? What all things does it tell? It tells you your country code, then operator code, area code, subscriber number, and all those things. And then we said that, okay, now we port our number from one network operator to another network operator. So how does that thing function? Because when we are porting a number, the numbers remain same, which means the operator code is not changing, but your operator is changing. So it was mentioned that for number portability, a database is maintained, and once you request the base station for connection, at that point it is checked whether the database is checked whether you are with the same operator, you have migrated to the other operator. We looked at how call gets connected, how a user is registered, and all those things. Then we had a brief introduction on duplexing techniques. Primarily, we looked at two different duplexing techniques. First one was your full frequency division duplexing. So here, what we say is the uplink and downlink transmission. So uplink and downlink transmission happens at different frequencies. So this is uplink transmission, this is downlink transmission, and this is time. Frequency. And we saw how the frame structure for an FDD GSM system look. We saw that the uplink and downlink bands are 45 megahertz apart and all those things. So we looked at the 900 megahertz band. Okay, then we looked at TDD. So for TDD, we said that instead of duplexing or having uplink and downlink transmissions at two different frequencies, let us transmit both of the signals on, or let the base station and the user transmit on the same frequency, but at different time instances. So that is something that we call as time division duplexing. So you are duplexed, but in time. So uplink will happen at some particular time instant, and then downlink will happen at another time instant, but on the same frequency. So this is on the same time. And here you have same frequency. We saw that in GSM, a combination or a small time offset is given for this FDD signal in order to avoid the overlapping or interference when you have multi-slot transmissions. I won't go into details of that. And then we looked at something known as CDMA. So CDMA here stands for code division multiple access. This is a multiple access technology. So this is code division multiple access. So in this, a unique code which is assigned to every user, and though two users codes are orthogonal to each other, so simultaneously on same frequency we can transmit the data to all the users, but they will be able to decode only their own data with the help of that unique code. Now the CDMA will be discussed with much more greater detail when we move towards the end of this course. So right now, very superficial introduction was given to CDMA, but it will be discussed in very much detail when we go towards the end of this course. After that, we looked at physical channels and logical channels. So physical channel is something over which we transmit the data. And logical channels are basically some things that are going to tell you where are you sending control data, where are you sending traffic data, and so on. So for logical channels, we have two categories. One is control and another is traffic. Traffic is the thing on which you transmit or the base station transmits the data packets. But for the control channels are something that are more important, which because they help you to connect with your base station, authenticate yourself with the base station, and all those things, page like request for connection and all those things. So we have broadcast control channel, which is BCCH, which is transmitted by the base station, which has operator ID, base station ID, local area net ID, and minimum receive power levels, maximum transmit power levels, and all those things. And this is broadcasted by the base station towards all the users. This is heard by all the users and understood by all the users in that particular cell. Then we have a common control channel. This particular control channel is used for paging and paging thing, and when you have to do downlink. Sorry, yeah. Okay, so in this control channel, this is transmitted by the base station. It is heard by all the users, but only one user will respond to the base station, and that will essentially connect to the base station. And then we have dedicated control channel. This is dedicated to one particular user once it gets connected, and all those things. Uh, the authentication and stuff is handled by the common control channel. And then we have RAT, that is random access control channel. So this is for uplink. So when you want to, when a user wants to connect to base station doesn't know that he wants to transmit some data or he wants to have some voice call. So now the user will start to send back information on the random access channel requesting for channel access. So that is done over a RAT channel. And then again we have this TCA traffic, that is TCH traffic channel. So this was basic idea about your channels, like logical channels. And then we moved on to physical quantities, or that basically aid you in communication aspects or transmitting your signal and how it works. So the first and most important part of any transmit receive structure is antenna, because that is the thing that is going to radiate your energy, and that is the thing that is going to catch your radiated energy. So for understanding level, or uh, we generally study something known as an isotropic antenna. So an isotropic antenna is essentially a point source. It is a point radiator, and it is a point radiator, so it radiates in all the three dimensions. So it radiates in all three dimensions equally. So this is the most ideal situation and in that we see, but many times we'll have an omnidirectional antenna, where this is an example of a dipole, and dipole generally looks something like this. So you have two poles, one here, and the radiation pattern that the dipole has is something like this. So it radiates equal energy along the horizontal plane. So we have equal radiation along horizontal plane. Then we looked at some quantity that is known as flux density. So what do you mean by flux density? So flux density is nothing but the power received by in a per unit area. So this is power received per unit area. So the flux density at a distance r is nothing but pt by 4 pi r square, and this is the quantity and this is for your isotropic antenna. So this comes when you have an antenna and you have a three-dimensional sphere around it with a radius of r. So the surface area is 4 pi r square. So the transmit power gets distributed equally around throughout this area. So that's why per unit area it is pt by 4 pi r square. And then we looked at something known as um, effective area. So effective area of a receive antenna is the area which is able to capture the transmitted energy. So for an isotropic antenna, for an isotropic antenna, effective area is lambda square by 4 pi, and your received power is proportional to your effective area. So with this basic knowledge, we then moved on to look at something known as path loss model. So how does your signal decay as we move away from the transmitter, and how much loss does it see? So in a large scale fashion or on an average fashion, this is given by your path loss models. And the very basic path loss model is for an isotropic antenna, which is nothing but your free space path loss model. So the received power at a distance d is given by the power flux density into the effective area. And since it is for an isotropic antenna, your power flux density was the transmit power upon 4 pi d square into the effective area we just wrote as lambda square by 4 pi. So this is nothing but pt into 1 over 4 pi d by lambda whole square. So this is your effective area, and this expression is essentially in decibels in linear scale. So your received power in decibel or dBW or dBm is your transmit power in dBm minus 10 log to the base 10 4 pi d by lambda whole square, and this is your path loss at distance t in dB. So this was your free space path loss model. Then we looked at another interesting path loss model, which is a breakpoint model. So in a breakpoint model, what do we say is, if I plot the expression for your receive signal strength at distance d as a function of d, log d, sorry, then you will see that for a particular time instant, your slope is going to be minus 2, slope of your path loss in minus 2, this is in dB. And after that, it will decay faster with a slope of minus n, where n is greater than 2. Such kind of models are known as breakpoint model, and the point where, or the distance where the slope changes is your d break or the break distance. So in this situation, the received power at distance d in linear scale is given by the received power at distance d break into your d break by d whole to the power n, and this quantity here is obtained based on your free space path loss model. So now if you want to write it in similar fashion, what you can get is your received power in dBm will be your received power at D break in dBm minus, I'll write it as 10 log to the base 10 d by d break to the power n. But received power at d break can be written from this particular equation, that is transmit power in dBm minus path loss at d break. So this is basically received power, transmit power in dBm minus path loss at d break in dB and 10n log to the base 10 d by d break. So now this second quantity after the minus sign is basically the entire path loss at distance t in dB. So this is your breakpoint model. After that, we moved on to look at link budget aspects. And the first thing that we looked at in this particular case was EIRP. EIRP is at your effective isotropic radiated power. And EIRP in linear scale is basically your transmit power that will get boosted by your antenna gain. Then if you have an amplifier, you can have an amplifier gain, and that will be hurt by your feeder loss. So here your PT is transmit power, then your GT is antenna gain, GA is your amplifier gain, and LF is the feeder loss. So this is in your linear scale. This is in your linear scale. The units for this are watts. So your EIRP in dBm will be your transmit power in dBm minus your, plus your antenna gain in dB plus your amplifier gain in dB minus your feeder loss in dB. So this is your link budget that we have seen. After that, we looked at outage. What do we mean by outage? Outage means the received power has, or the power with which you are receiving a signal is less than a threshold, and the threshold is something. So if your received power is less than that that your received power is less than some threshold, which equivalently translates to your path loss is greater than some average path loss plus some additional margin that is added for taking care of the random fading. Then we moved on to discuss another important concept of noise figure. So noise figure is, by definition, it is SNR at input. SNR is signal to noise ratio upon SNR at output. And we also looked at in case we have cascaded systems. So if we have a system with gain G1 and noise figure F1, then we have another system with gain G2, noise figure F2, then we have G3 with noise figure F3, and so on. Then the overall noise figure will be given by the noise figure of first stage plus the noise figure of second stage minus 1 divided by the gain of the previous stage, that is G1, plus noise figure of the third stage minus 1 upon the product of gains of all the previous stages, that is G1 into G2 and so on. So this is for your cascaded case. After that, we looked at something known as the noise limited systems. So in a noise limited system, here I am plotting the receiver level. The signal decays with distance. This is distance. This is where you are transmitting. This is your transmit power. And then you will have a noise floor. And then you will have something known as receiver sensitivity. And this distance is basically your SNR, minimum SNR. And if your signal goes below the receiver sensitivity, you can't transmit. So this particular point at which your received signal crosses the receiver sensitivity or goes below the receiver sensitivity, this is the maximum distance till which you can transmit. After that, you can't transmit anywhere. So here the term or the quantity that we define is signal to noise ratio. For example, if we have the signal component here, then this entire thing is your signal to noise ratio or SNR, and this is what we consider as a metric to evaluate this thing. Here only noise is present or the noise is dominating, so therefore such systems performance is limited by the noise. So therefore these systems are known as the noise limited system. And there is another kind of system which is interference limited system. So in an interference limited system, we have one more base station which is transmitting at this on the same frequency. So we had the previous system which was transmitting and its signal was decaying, and then we'll have another system which is located at far and its signal strength will be something like this. So yeah. So again here we'll have noise. We'll have noise floor and we'll have receiver sensitivity. But at the same time, this particular signal is also going to affect you especially when you are lying in this region. So here in this region, your your interfering signal has a higher signal strength compared to your transmitted signal or your desired signal. So this is from adjacent base station, or rather interfering base station, and this is from your own base station or rather desired signal. So instead of having a Dmax here, we'll now have a Dmax before that, so that we allow for minimum SINR. So your Dmax shrinks. So if there is no interference, your Dmax would have been here. Now it shifts, and the quantity that now we define is not SNR, but it is SINR. And what does this SINR stand for? SINR stands for signal to interference plus noise ratio. And so this is SINR is nothing but signal to interference plus noise ratio. When this noise is not dominating much, and when you can approximate this SINR to C by I, which is nothing but your SIR, signal to interference ratio, then such a system is known as interference limited system. Because the system's performance is predominantly affected or limited by the interference and not by the noise. And the last thing that we looked at is the cellular concept. We introduced the cellular concept. We introduced the 9 factors that the McDonald's paper requested. I won't go into details of that. And yeah, so in that we said that we'll divide the entire region into cells. We'll also do cell splitting, and we'll also use cluster them and repeat the frequency allocation patterns over the distance, that is known as frequency reuse. The valid cluster size you looked at, that is I square plus j square plus ij, where I and j are integers, and we also seen how the C by I ratio is calculated. I'm not going into details of cellular concept right now. We'll solve questions, and at that time we'll discuss more into this. But maybe before going ahead, I'll just note down some key terms in cellular concept. So key terms in cellular concept. So the first one is number of channels per cell, and that is given by K. Then we have number of cells per cluster, that is N. So based on this, the total spectrum available in a cluster, that is number of channels per cluster, is Nk. Then we have area of a cell, that is A. And we said that the hexagonal structure is the cell structure that has the best area coverage. We saw how it comes. Then repetitions of clusters, that is M. So based on this, the total area covered is number of repetitions of clusters into number of cells per clusters into area, and the capacity or total capacity will be number of clusters into number of cells plus per clusters into number of channels that are used per cell. Another important factor is co-channel reuse ratio. This is d by r, which is also q, which is under root of 3n, and this distance d is basically the distance between the co-channel interfering cells. Okay, so we'll solve the questions that are related to this week's content. If you have any questions, please let me know. So that's all about the recap. Okay, so before starting with the questions, I'll have a quick digression today. Because towards the end of the last week's tutorial, someone asked me a question of how EB by N naught ratio is related to PS by PN ratio, which was discussed in last week's content, but apparently that was not clear. So the whole idea started uh, with the notion of programming assignments, in which the bit error rate versus EB by N naught was asked to plot. And if you look at the books such as Proekis and all those things, generally the BER versus EB by N naught is plotted. So in general, if you see any books, BER versus EB by N naught is plotted for an AWGN channel. So here what is EB? EB is energy per bit. Okay. Now, how do you relate energy with power? So energy is basically power into time. So the power consumed, energy per bit is will be equal to the transmit power, that is, let's say PS into TB, where PS is the transmit power and TB is the duration of a bit. Okay, so this is what we have for your EB. Now the second thing that we have is N naught. What is N naught? N naught is not noise power. It is basically noise power spectral density. So this is noise spectral density. And what are the units of power spectral densities? This is in watts per hertz. So this is basically the noise, the power per unit bandwidth. So if BEQ is the equivalent bandwidth with which you are transmitting a symbol, then the noise power which is your noise power will be equal to N naught into bandwidth. And generally the pulse shaping filters that you use help you to restrict your bandwidth in such a way that it is equal to 1 over your symbol duration. So examples of pulse shaping filters are square root raised cosine filters and all those things. So generally your BEQ is approximately equal to 1 by Ts, where Ts is duration of a symbol. So therefore your noise power becomes N naught by Ts, or in other words your N naught is equal to Pn into Ts. So from equation 1 and 2, what do we have? EB by N naught. So EB was equal to PS into TB, and N naught is Pn into Ts. So this is basically PS by Pn into TB by Ts. So the second one is the ratio of bit duration to symbol duration. So now if one symbol has k bits, then it implies that Ts is k times TB. So therefore this EB by N naught is basically PS by Pn into 1 by k, where k is the number of bits per symbol. So if you have a BPSK system in which number of bits are 1, your EB by N naught is equal to your PS by Pn. If you are using a QPSK, then you have 2 bits per symbol. So your EB by N naught becomes PS by Pn into 1 by 2 and so on. So I hope this addresses your question. And if you have any question in this part, please let me know. I'm able to see another question in the chat box, which is asking me to explain the outage again. Okay, so in a wireless scenario, everything is changing. Okay, so because your vehicles are moving, you have trees, you have buildings and all those things. So generally what happens is your received signal is a fluctuating quantity which looks something like this, or to be, yeah, which looks something like this with distance. Okay, instead of having a straight line, something like this. But my receiver sensitivity is somewhere here. Okay, so this is the minimum received power with which my receiver can sense. Anything below that it can't sense. Okay, so now the question is, okay, so what do you mean by outage? Whenever my received power goes below this threshold, then we have outage. Does that make sense to you? Equation of what? This is outage. Now, since your signal is a random quantity, so at a given time instant, you can have different curves of these things. So instead of having a standard notion of outage, like after a particular span, you don't know exactly how you're going to receive. Your noise is also random and all those things happen. So instead of understanding outage, you say something known as probability of outage. So this is probability that your received power is less than your receiver sensitivity or some threshold. This is the basic equation for outage. We'll get into outage when we discuss fading in more detail. So hold on to this fact for now. I think in coming week we'll be seeing more on this when we look at shadowing and fading. So for equations, you wait. Yeah, thanks. Any other question? Okay, if there are no questions, then let me quickly move on to the first question that I want to cover today. Okay. So the first question for today is, a base station is equipped with an antenna of gain 3 dB. So the first quantity given to us is antenna gain, which is 3 dBi. So what does this I mean? So this I means this ratio or this gain ratio is with respect to your isotropic antenna. That's why that I. So we have a base station is equipped with an antenna of gain 3 dBi. The antenna is fed with a 100 milliwatt power. So the transmit power is 100 milliwatt, and this is fed through an amplifier of 15 dB. So then you have an amplifier with gain that is 15 dB. If the feeder loss is 4 dB, so feeder loss is 4 dB. What do we want to find? We want to find EIRP in dBW and dBm. Okay, so this is what we have. So since we want to find the things in dBW and dBm, we'll first do it in dBm. Because the power that is given to us is in dBm. So this transmit power in dBm will be given by 10 log to the base 10, 100 milliwatt, or power in dBm 100, that is equal to your 20 dBm. So therefore, by definition of EIRP, in dBm will be your transmit power in dBm, sorry, this is dBm, yeah, plus your antenna gain in dB or dBi, plus your amplifier gain in dB, minus your feeder loss in dB. So your transmit power in dBm is 20 dBm, plus you have your antenna gain of 3, plus you have amplifier gain of 15 dB, and minus you have your feeder loss. So this is equal to 34 dBm. So this is what we found in dBm. So therefore, EIRP in dBm is 34 dBm. And if I want to convert this dBm to dB, what do? We subtract 30 from it. So EIRP in dBW is EIRP in dBm minus 30. So this is 34 minus 30. That comes out to be equal to 4 dBW. Okay, is it clear? Any questions? Okay, if there are no questions, then let me move on to the next question. Okay, so the next question is related to your noise figure. So it says that if the noise figure of the first stage of a two-stage cascade network is 8 dB and the noise figure of the second stage is 7 dB, the gain of the first stage is 10 dB, then the noise figure of the cascaded system is what? So what is given to us? You have a two-stage cascaded system. The noise figure of your first system is 8 dB and gain is 10 dB. And the noise figure of the second stage is 7 dB. And what do you want to find is what is the overall noise figure. Okay, so this is the question that we want to answer. Okay, so what is the expression for overall noise figure? So this is noise figure of the first stage plus noise figure of the second stage minus 1 divided by the gain of the previous stages. Okay, so now are we going to substitute this 8 dB, 10 dB, 7 dB in this equation? No. If you directly substitute the dB scale or the logarithmic scale values in this equation, you will get completely wrong answers. Because all the values in this equation, so the F1, F2 and G1 values in this expression should be in linear scale and not in dB. Okay, so whenever you are given such kind of things, first thing that you need to do is first you need to convert them to linear scale. So every time the step 1 is convert dB values to linear scale. So let's do that. So we are given the noise figure of the first stage in dB as 8 dB, which means that, so how do you go back to your linear scale? So this F F1 in dB is basically 10 log F1 in linear scale to the base 10, which means that your F1 in linear scale will be 10 to the power F1 dB divided by 10. Okay, so therefore this comes out to be equal to 10 to the power 8 by 10. For this you use your calculators, which will be provided to you in your exam. So this will be equal to 6.31. Then you have F2 in dB, which is equal to 7 dB. So therefore your F2 is nothing but 10 to the power F2 in dB divided by 10, which is equal to 10 to the power 7 by 10, which comes out to be equal to 5.01. And the last one was your gain G1 in dB, which was given to us as 10 dB, which means that your G1 is 10 to the power G1 in dB divided by 10, which is 10 to the power 10 by 10, which is nothing but 10. Now we are good to go, and we can substitute these values, linear values, in your overall noise figure expression. So therefore, the overall noise figure is F1. F1 is 6.31 plus you have noise figure of the second stage 5.01 minus 1 divided by gain of the previous stage, that is 10. If you simplify this turns out to be 6.711. This is again in linear scale. So now if you want to convert this to dB, then you can do this. So this will be equal to 10 log to the base 10 F overall in linear scale, which is 10 log to the base 10, 6.711. This comes out to be equal to 8.27 dB. Is it clear? Any questions? Okay. If there are no questions, then let me move on to the next question. So what is given to us is consider a breakpoint path loss model. Consider a breakpoint path loss model with D break as 50 meters. So your break distance is so your D break is 50 meters and path loss exponent after D break is 3.7. So the path loss exponent is 3.7 after D break. Suppose a base station is operating at a carrier frequency of 1850 megahertz. So the carrier frequency is 1850 megahertz and is capable of covering a range of 2 meters beyond the breakpoint. So the maximum distance that base station can cover is your D break plus 2 meters, that is 50 plus 2, that is 52 meters. Beyond what is the maximum path loss the base station can? handle. So what is the maximum path loss that the base station can handle? So how does the path loss look? If you go back to our revision, so for a breakpoint model, the path loss in dB is equal to the path loss at d break plus 10n log to the base 10 d by d break. At distance d max in dB is path loss at d break in dB plus 10n log to the base 10 d by d break. Okay. So what is 10n log 10? What is let's do it term by term. So let's do the second term first. So 10n log to the base 10 d by d break into log to the base 10 d max. So this should be d max d max is 52 meters and d break is 50 meters. If you simplify this, this comes out to be equal to 0.63 dB. Then the first term is your path loss at d break at in dB, that is 10 log to the base 10. You have 4 pi d break by lambda whole square. What is lambda? Lambda is your wavelength. Did we find out wavelength? No, but we are given carrier frequency. So how do you get wavelength from carrier frequency? That is C by Fc. C is speed of light. So this is 3 into 10 raised to 8 upon 1850 into 10 raised to 6. And if you use calculators, this comes out to be equal to 0.162 meters. Okay. So now if you substitute it here, we have 10 log to the base 10, 4 pi, your d break is 50 and wavelength is 0.162 meters whole square. So this comes out to be equal to 71.77 dB. Therefore, the total path loss or the maximum path loss at the maximum distance is path loss at d break, that is 71.77 plus your 0.63, that is the second term of this expression, and this comes out to be equal to 72.40 dB. Is it clear? Any questions? Okay. If there are no questions, then let me move on to the next question. So the next question here says that suppose an indoor LAN with a carrier frequency of 900 megahertz is equipped with an omnidirectional antenna that transmits with a minimum transmit power of 15 milliwatt. If it covers an area of radius 20 meters, find the received power assuming the free space path loss model. Okay, so what all things are given to us? So the first thing given to us is carrier frequency. So carrier frequency is 900 megahertz, which means the wavelength lambda, that is c by fc, that is 3 into 10 raised to 8 upon 900 megahertz, that is 900 to 10 raised to 6. This comes out to be equal to 1/3 of a meter. It is equipped with an omnidirectional antenna that transmits with a minimum transmit power of 15 milliwatt. So transmit power is 15 milliwatt. So your transmit power in dBm is 10 log to the base 10, 15 milliwatts, which comes out to be equal to 11.7609 dBm. So this is in your dBm. Then what is given to us, that if it covers an area of radius 20 meters, then find the received power. So the distance d is 20 meters. Then find the received power assuming free space path loss model. So what do we have? The received power at distance d in dBm is given by your transmit power in dBm minus the path loss at distance d. So transmit power in dBm we already found out as 11.7609 dBm minus path loss in dB. So how do you find the path loss? So path loss in dB is equal to 10 log to the base 10 path loss in linear scale. This quantity is equal to 4 pi d square by lambda, because we are going to use the free space path loss model. So therefore this is equal to 10 log to the base 10 4 pi d square by lambda whole square, 4 pi d, not d square, sorry, whole square, yeah, 4 pi d by lambda whole square. So this turns out to be equal to 10 log to the base 10. We have 4 pi, the value of d is 20 meters and lambda is 1 by 3 whole square, and this comes out to be equal to 57.5472 dB. So therefore the received power at distance d in dBm is equal to 11.7069 minus 57.5472. This comes out to be equal to minus 45.7863 dBm. Any questions? Okay, let's move on to the next question then. Okay. So the question here says that consider a cellular network built with 7-cell cluster structure with base stations transmitting at carrier frequency of 5 gigahertz and power of 1.5 kilowatt. Just a minute. Yeah, okay. Yeah. Okay, so the number of cells per cluster. So the first piece of information is number of cells per cluster is n, that is 7, and the carrier frequency is 5 gigahertz, which means the wavelength is 3 into 10 raised to 8 upon 5 into 10 raised to 9, which is 0.06 meters. Then the radius of each hexagonal structure is 2 kilometers. So radius of cell, that is R, is 2 kilometers. Then it says assume a single breakpoint model with D break as 1 kilometer. So path loss model is breakpoint with D break as 1 kilometer and path loss exponent as 4.2. Then the question that is asked to us is find the co-channel reuse ratio. So what is the co-channel reuse ratio? When we noted down the parameters or key terms in cellular concept, the co-channel reuse ratio is given by D by R, or it is also equal to under root 3n. So co-channel reuse ratio co-channel reuse ratio Q is under root 3n, which is equal to under root 3 into n is what? 7. That is under root of 21, which comes out to be equal to 4.58. That's all was asked in this question, and they had given a lot of noise and lot of parameters. The only parameter of the of our use was n equal to 7. Rest everything was useless for this particular question. So it might happen that in your question too much information is given. Don't get confused. The question can be as simple as find the co-channel reuse ratio, which depends only on one parameter in the given listed parameters. So that's all about this particular question. Any queries? So what we are going to do is we have these set of parameters. So now we'll spend some time on some questions which are related to your cellular concept. So we'll make use of these parameters and we'll solve 2-3 questions which are essentially related to your cellular concept. So for that, let us first look at a 7-cell cluster structure. So a 7-cell cluster structure looks something like this. So you have a cell here with a base station located at the center of the cell, and you have 6 co-channel interfering cells which are around it, and the distance the distance from here to center of any of these base stations or is given by d. So essentially, if we just focus on this particular thing, so this distance is d. This distance is r. Okay, and based on the first order approximations, the distance between this thing to uh, this base station is t plus r by 2 and so on. So this is obtained assuming your r is smaller than d. So these distances are calculated by assuming d by r is much smaller than 1 or smaller than 1 at least. Okay, so this is how your 7-cell structure looks, and these are the distances that you can try calculating once on your own. If you don't get it, then you can ask me in the next class. I'll maybe do a small example for you. Let us just calculate this distance x which I have written. So you can write this distance x. So just focus on this triangle which I have marked. So here your distance x is given by this distance, that is x1, and this distance, that is x2. So your x is basically x1 plus x2. Or in other words, what you can do is, you want to find this distance x, so you can apply cosine rules with this angle theta. So your x square, so using law of cosines, your x square will be equal to d square plus r square minus 2dr into cos theta. And if you see, this theta is basically 30 degrees. Sorry, not 30, 60 degrees. So this is basically half. So this comes out to be equal to minus dr. And then x is under root of d square plus r square minus dr. I can pull out d outside, then I'll get 1 plus r square by d square minus r by t to the power half, which is approximately equal to d 1 plus r square by 2d square minus r by 2t, and ignore all the terms which have d square in the denominator. So any second order term you ignore. So this is approximately equal to d minus r by 2. Sorry, there should be a plus sign somewhere. Yeah, some mistake. Sorry, yeah. Yeah, some mistake I did. Okay. So something like this you will land up into here. Okay. So make use of such techniques to get to those distances. You can find these detailed derivations in Rappaport. It's there. So based on this, the first question that we want to find out is, find the distances from the user and all the tier 1 interfering base stations. So all these base stations are tier 1 interfering base stations. Okay, so you want to find out what exactly is the distance. Yeah. So you want to find out what exactly are these distances. So these distances depend on two factors, that is d and r. In your previous question, you are given r, but you don't have d. But what you know is your co-channel reuse ratio. So we'll make use of that. So co-channel reuse ratio is d by r, which is also equal to under root of 3n, which we had obtained in the previous question, that is 4.58. So therefore your d is equal to 4.58 into r, and r is 2 kilometers. So 4.58 into 2, that is 9.16 kilometers. So now we know the distances. So what we will do is, let's say we need to find all these distances, so we'll number these. Okay. Okay, so we have this. So the first distance, that is, let's say d1, d2, d3, d4, d5, d6. So d1 is your d plus r, that comes out to be equal to 9.16 is your d, plus r is 2 kilometers, that is 11.16 kilometers. Then your d2 is d plus r by 2, this is approximations. This is basically equal to 10.16. So d is 9.16 plus 1, that comes out to be equal to 10.16 kilometers. Then you have d3, which is approximately equal to d. This comes out to be equal to 9.16 kilometers. Then you have your d4, which is equal to d minus r, which is 9.16 minus 2. So this is 7.16 kilometers. You have d5, which is again d minus r. This comes out to be equal to 7.16 kilometers. And then you have d6, which is d minus r by 2, that is 8.16 kilometers. Sorry, this cosine rule is wrong. Yeah, wait. This is not making sense. The angle opposite to this x is this quantity. So this is your 120 degrees. So you have x square to be equal to r square plus d square minus 2rd cos of 120 degrees, and cos of 120 is minus half. So r square plus d square minus 2rd into minus half. So this is basically r square plus d square plus rd. Now you pull out your d, x equal to, so your x is equal to under root of this. So now you pull out your d, then you will have 1 plus r square by d square plus r by d. Yeah, to the power half. And now in order to simplify this, you can use 1 plus x to the power half is approximately equal to 1 plus x by 2. This is first order Taylor series approximation. So you will get d into 1 plus r square by d square plus r by d half. And this is approximately equal to d in So this you can ignore, second order term. So what you are left with is d plus r by 2. Yeah, so in this fashion you need to find all of these things. Sorry, this derivation was not making sense to me, so I revisited it. So again, let me go back to this question. So based on this Taylor series approximation, first order approximations, we have obtained these d1 to d6 distances as highlighted in this figure, and based on that we can substitute the value of d and r in these 6 distances and calculate uh, these distances essentially. But in order to find these 6 values, we need to know 2 quantities, that is your d, that is distance between the base station from its adjacent or co-channel interfering tier 1 base station, and the cell radius. Cell radius we know, it was given in the question, but what we didn't know was the value of d. But we know the relation between dr and one more quantity, that is channel reuse, co-channel reuse ratio, which we had already found out in the previous question, which was under root 3n, which turned out to be 4.58. So based on that, we can calculate what is the value of d. We already know what is the value of r, and based on that, we were able to calculate all these 6 instances. Any questions? Okay, if there are no questions, then let me move on to the next question. So it says that in the previous question, find the worst case SIR, signal to interference ratio. So SIR, sorry, which is your signal to interference ratio, this is equal to your received power from the desired base station divided by summation of I equal to 1 to, we'll just focus on 6 co-channel, like tier 1, received power from ith interfering base station. So this is PRX from of your current thing divided by summation I equal to 1 to 6 PRX of I. Okay. So what is PRX of 0? So if you go back to your previous question, that is question number 5, we are given that we need to use the breakpoint path loss model. So PRX of 0, this will be at a distance of, so if you go back here, so you have your desired base station located here, and the distance from the base station to the cell edge user is r. So your received power from your desired location has to be measured based on the distance r. So this is your transmit power into your received power at d break into d break by r to the power n, or in other words I can also write it as transmit power into PRX d break into r power n, r power minus n into d break d break power n into r power minus n. Similarly, Prx of I, this is the received power from ith interfering base station. So the distance of this particular user from, let's say, the second base station is this d2. So its distance from the ith base station, ith interfering base station, is basically di. So now your receive power has to be calculated based on the distance di. So you'll have transmit power into your receive power at d break into you have d break by di whole to the power n, which is equal to pt into receive power at d break into d break to the power n into di to the power minus n. So now if I substitute these things in your SIR equation, so therefore the signal to interference ratio is equal to your PRX0, that is PT into PRX at D break into D break to the power n into di to the power minus n divided by summation I equal to 1 to 6. We have PT into PRX into D break. This is R. D break to the power n into di to the power minus n. Now from the denominator, I can pull out these factors. These are common. So this is equal to PT into received power at breakpoint into breakpoint to the power n into r to the power minus n whole divided by Pt into received power at breakpoint into d break to the power n into summation I equal to 1 to 6 di to the power minus n. So these are common factors, these get cancelled. So what we are left with is the signal to interference ratio is r to the power minus n divided by summation I equal to 1 to 6 di to the power minus n. Okay, so what is the value of r? R is 2 kilometers. So this is 2 to the power minus n divided by, you have all the 6 distances that you had calculated in the previous question. Those are these 6 distances. So we'll substitute all of these in the equation below, or in this particular equation. So this is equal to your D1 was 11.16 minus n. So here n is 4.2, I think. Let me go back and check. Yeah, so the path loss exponent is given to us as 4.2. Plus your D2 is 10.16 to the power minus 4.2 plus 9.16 to the power minus 4.2 plus 7.16 to the power minus 4.2 plus again 7.16 to the power minus 4.2 plus 8.16 to the power minus 4.2. The numerator value is 0.0544 divided by 8.5158 into 10 raised to minus 4, and this turns out to be equal to 63.8816, and this is in the linear scale. So therefore again we can convert it to the decibel scale or dB scale. So your signal to interference ratio in dB scale is 10 log to the base 10 into SIR, that is 63.8816, and this comes out to be equal to 18.9 0.054 dB. Okay, so this is your signal to interference ratio. Okay. Okay, so the next question is find SINR if the noise floor is minus 119 dBm and noise figure is 15 dB. The system is noise limited or interference limited. Okay, so what is SINR? So SINR is your signal to interference plus noise ratio. So this is equal to your received power from the current base station or actual desired base station plus your interference power, that is PRX I, plus your noise power. So this is your SINR. Okay, and we want to find out this, and this PN is basically your noise power. Now if I manipulate this, so basically if I divide numerator and denominator with PRX 0, this comes out to be equal to 1 over summation I equal to 1 to 6 PRX I divided by PRX 0 plus Pn upon PRXO. Okay. Now this I can equivalently write as 1 over 1 divided by PRX 0 divided by summation I PRXI plus 1 divided by PRX 0 divided by Pn. Now this quantity by definition is the signal to interference ratio, and this quantity is basically signal to noise ratio. So this we can write as 1 upon 1 by SIR plus 1 by SNR. Okay. So SIR we obtained in the previous question, and that was equal to 63.8816. Just a moment. So this comes out to be, so therefore 1 divided by SIR comes out to be equal to 0.01516, something like this. Now what we want to find out, so SIR and 1 by SIR we know, but what we want to find out is 1 by SNR. So 1 by SNR is basically Pn upon PRX 0. So received power we know, it is given to us. Still, let's calculate it. So your noise power in dBm is basically your noise floor in dBm plus noise figure in dB. So this comes out to be equal to minus 119 plus noise figure is 15. So this is minus 104 dBm, or when you want to convert from dBm to dBW, you subtract 30. So this is minus 134 dBW. So therefore your noise power in linear scale is 10 to the power Pn in dBm or dBW divided by 10. 10 to the power minus 134 divided by 10, or 10 to the power minus 13.4. So this is the first thing that we have. Now what we want to find out is your receive power. For receive power, we had seen that the expression is something like this. That is transmit power into breakpoint thing into this quantity. So I'll just copy paste this. So based on the breakpoint model, leave it. So using the breakpoint model, PRX0 is your transmit power into PRX at D break into D break by D to the power n, or to R to the power n. So transmit power is given to us as 1.5 kilowatt. So this is 1.5 kilowatt, or yeah, into PRX of D break is nothing but lambda upon 4 pi D break whole square into D break by D to the power n. So this is 1500 into lambda we had calculated in the first part in question 5. So this is lambda is 0.06 meters, D break is 1 kilometer, R is and n is 4.2, path loss exponent. So lambda is 0.06 meters upon 4 pi, D break is 1 kilometers, so 1000 meters whole square into D break is 1000, distance here we have R is 2 kilometers, it is 2000 meters to the power 4.2. And if you simplify this using calculators, this comes out to be equal to 1.806 into 10 raised to minus 9. So therefore 1 by SNR comes out to be equal to your noise power. So Pn is 10 to the power minus 13.4 divided by 1.806 into 10 raised to minus 9. So this comes out to be equal to 2.1397 into 10 raised to minus 5. So what all we have? We have 1 by signal to interference ratio as 1.565 into 10 raised to minus 2. 1 by SNR is 1.806 into 10 raised to minus 9. So therefore SINR is 1 over 1 by SIR plus 1 by SNR, which is equal to 1 upon 1.565 into 10 raised to minus 2 plus 1.806 into 10 raised to minus 9. So what do we get is, so we have 1.565 into 10 raised to minus 2 plus 1.806 into 10 raised to minus 9. Just a minute, 1 second. Sorry, I made some calculation mistakes in my notes. Give me a moment. Yeah, okay, so this turns out to be equal to 63.8977. So your SIR, which we had obtained in the previous question, was 63.8816, and your SNR is basically your 1 over okay, it's okay. So now if you compare it, what we are able to see is your SINR and SIR, these are comparable. So here your SINR is approximately equal to your SIR. Reason being, if you compare these two, 1 by SIR is much greater than your 1 by SNR. So when you use this idea and plug it in here, so your SINR, you can approximate it to be 1 over 1 by SIR. Why? Because this quantity is much smaller than this particular quantity. So therefore you can ignore this. This is the dominant quantity, and therefore your SINR is approximately equal to 1 over 1 by SIR, which is this. So this quantity is equal to your signal to interference ratio. So now if your SIR and your SINR are comparable, your noise is not impacting your system at all, or it is impacting but not too much. Or in other words, your interference is limiting the system's performance. So therefore, this particular system is interference limited system. So this is an interference limited system. Is it clear? Any questions? So we found out the SNR, we compared, found out SINR, we compared it with signal to interference ratio. And since SINR and SIR are comparable, this is an interference limited system. Any questions till now? Okay. If there are no questions, then let me move on to the next one. So it says that which of the following are the valid choice of cluster? So which formula gives you the valid cluster sizes? So the valid cluster sizes are given by I square plus j square plus ij, where I and j are positive and non-negative integers. So they can take any values from 0, 1, 2, 3 and so on. Okay, so this is the scene. Now there is no way of or no algorithm to find out which are the valid cluster sizes or not. It is purely trial and error basis. So what turns out is 7, we know 7 is a valid cluster size, and we had seen two options for this. The first one is I equal to 1 and j equal to 2, for which we can have, and another was I equal to 2 and j equal to 1. For both of these choices, we'll have I square plus j square plus ij. So 1 plus 4, 5, 5 plus 2, 7. So these are the two choices for this. Then we have seen 3. How can we obtain 3? 3 can be obtained if you set I equal to 1 and j equal to 1. This is one choice. You can also put I equal to 0 and j equal to 3 and so on. So this is one option. So when you have this, you will have 1 square I square plus 1 square, that is j square, plus ij, that is 1 into 1, 1. So this turns out to be 3. So this also has a combination or values of I and j, integer values of I and j that can have. Then for 16, we have I equal to 4 and j equal to 0. In that case, we'll have 4 square plus 0 square plus 4 into 0, 0. So this turns out to be equal to 16. So again, 16 is also a valid choice. And similarly, if you want to go for 4, you can set I equal to 2 and j equal to 0. So this will be 2 square plus 0 square plus 2 into 0, 0. That turns out to be equal to 4. So 7, 3, 16 and 4 are valid choices of clusters. But I had deliberately left out this 15. This 15 you can try out. There is no combination of I and j, integer I and j, that will lead to 15. So no combination of I and j that will lead to a valid cluster size as 15. This is purely based on trial and error. You need to try and substitute values. Is it clear? Okay. If there are no questions, then let me move on to the next question. So the question here says that the base station is transmitting with a power of 20 milliwatts and the user measures the received signal power at minus 105 dBW. If the carrier frequency is 1800 megahertz and considering the free space path loss model, what is the distance between the base station and the user? So the first thing given to us is the transmit power, this PT, that is 20 milliwatts, that is 10 log to the base 10, 20 dBm. This I can write as 10 log to the base 10, 10 into 2, which is 10 log to the base 10, 10 plus 10 log 2 to the base 10. Now note that this quantity is equal to 10 and 2 in dB scale is 3 dB. So these are the two quantities that you should in general remember. So this is basically 13 dBm. So you have the transmit power. Then what is given to us? The user measures the received signal power as minus 105 dBW. So received power at some distance d in dBW is minus 105 dBW. So therefore the received power in dBm will be dBW plus 30. So minus 105 plus 30 dB. So this is minus 75 dBm. Then the carrier frequency is 800 megahertz. So carrier frequency is 800 megahertz. So therefore wavelength is C by F, which is 3 into 10 raised to 8 divided by 1800 into 10 raised to 6, which is 3 by 18 meters, which is nothing but 1 by 16 meters. Then what is given to us? Considering the path loss, free space path loss model, we need to find what is the distance between the base station and the user. So this is the question that we want to answer. So what do we have? We have free space path loss model, and based on any path loss model, we have a relation between your receive and your transmit power. So your receive power at distance d in dBm is given by your transmit power in dBm minus the path loss in dB. Path loss at distance d in dB. So therefore, the path loss at distance d in dB is given by the transmit power in dBm minus the received power at distance d in dBm. So the transmit power in dBm is 13 dBm minus the received power at distance d is minus 75 dBm. So this is equal to 88 dB. Okay. So this is the first thing that we have. Now, what is the standard equation for a free space path loss model? So for a free space path loss model, path loss at distance d is given by 4 pi d by lambda whole square, and that in dB scale is 10 log to the base 10 into 4 pi d by lambda whole square, and this quantity is equal to 88 dB. So therefore what we have log to the base 10, or rather 20 log to the base 10 4 pi d by lambda is equal to 88. So log to the base 10 4 pi d by lambda is 88 by 20, that is 44 by 10, which is nothing but 4.4. So therefore 4 pi d by lambda is 10 to the power 4.4, and therefore d is equal to lambda by 4 pi into 10 to the power 4.4. This is the distance between the base station and the user. Therefore, d is equal to 1 by, sorry, we'll just repeat the formula. Lambda upon 4 pi, 10 raised to 4.4. So lambda was what? Wavelength. And wavelength we had obtained as 1 by 6. So this becomes 1 by 6 into 4 pi to the power 10 to the power 4 into 10 to the power 4.4, and this turns out to be equal to 333.15 meters, or this is equivalent to 0.33315 kilometers. So this is the distance between the base station and the user, which was asked in this particular question for free space path loss model. Any questions? Any queries? So this was the last question that I wanted to cover today. If you have any queries in any part of today's tutorial, feel free to ask. I'll be here for a few minutes. Okay, again, as a part of logistics, I'll upload these slides to the Google Drive folder in maybe 5 minutes after the end of this session, and the video will be uploaded on YouTube in maybe half an hour to 1 hour duration after the end of this session. The link for both of these is given to you in the bottom left corner of your NPTEL portal. There is a tab for problem solving sessions. You can go and click on the link there. You will find the links for recorded videos as well as the tutorial slides. And for video playlist, I have also pinned a comment in the chat that will direct you to the playlist. Please give me a feedback if this pace is okay, or I'm going too fast, or it's slow. Then accordingly I'll change in the coming sessions. Do let me know.
It's okay.
Okay, yeah, thanks. Okay, if you have any questions, then please continue asking. If you don't have any questions, then you're free to leave the meeting. Thank you for attending today's session. We'll have another session next week on Saturday around the same time, that is 5 to 7 p.m.
Okay, thank you.
Yeah, thank you.